Thanks, everybody. It's good to see a lot of familiar names, also from people from other institutions on here. Guess it's an added benefit of going online. So today, by the way, so I'm going to be broadcasting through screen sharing. If anything goes wrong or if you can't see anything, just let me know. I don't exactly know what you're seeing. So, well, this is still a trial run. So,
Adam, are you recording?
I believe I'm recording. Yeah.
Okay, thank
you. Yeah. Okay, so what I'm going to talk about today is based upon still some work in progress. So that's a bit of a disclaimer. I don't think we've totally understood everything there is to understand on this project, but I'm going to try and tell you what I think we do understand. And it's based on work with myself, Arvind Shabazi Mogadam, who is a grad student at Berkeley, soon to be a postdoc at Stanford, and Ronak Soni, who's also a postdoc at Stanford. Okay, so what am I going to talk about today? I'm going to try and talk about how one might be able to see behind the causal horizon, so in an optimal way. So I'm going to explain what I mean by that. But first, what do I mean by seeing behind the causal horizon? Well, what I mean is in the sense of traversable wormholes. So I'm just going to start with the review of traversable wormholes just to set the scene, and then I'm going to move into what will be the main topic. So just to remind you, I'm sure a lot of you remember this, but in the setup of Gao-Jaffer's wall, or also Maldacena, Stanford, and Yang, what we had was a two-sided thermal field double black hole, right, like this. And normally, if someone on the left sends in an excitation, this excitation will always end up hitting the singularity, and it won't reach to the right-hand side. This is good because there was no coupling between the left and the right, and there's just entanglement, which does not allow you to actually transfer information without an explicit coupling. But the work of Gao-Jaffer's wall showed that there's a nice way of actually getting this left excitation to sort of causally appear on the right. And the way you do that is you add to the Hamiltonian, you deform the Hamiltonian by a non-local operator that sort of looks like the form. So you add, so effectively what you do is you add to the path integral a term or a factor that looks like e to the I lambda times some operator k. Lambda is a coupling, and k I'm going to think of as an integral over both space and time of a left-sided operator times a right-sided operator. And there are a few comments. It's important for this protocol to work out that the left and the right operators are highly correlated, right? If O left and O right had zero correlation, this would not work. And what happens when these operators are correlated is that you send in a pulse of negative energy. Now, the details of how you do this coupling, so I should add in some smearing function here. The details of the smearing function tell you exactly what the energy profile looks like. But in certain limits, it just looks like a shock that's being sent in, a negative energy shock. And if you zoom in on the collision of what happens between this right moving excitation and this negative energy shock, what you get is a left moving excitation, a right moving excitation, a shock propagating in, and then a shift. This particle just gets shifted. And in x plus and x minus coordinates, sorry, other way around, x minus and x plus coordinates, this particle gets shifted by an amount delta x minus, which is proportional to the total null energy of this shock. So where I'm integrating along the horizon. And what Gauss-Jaffers-Wald pointed out was that when you do this by local coupling, this total integrated null energy can actually be negative. So what this means is that instead of getting a time delay, this particle can get a time advance. And this is what allows this particle, so if I follow its trajectory, it gets shifted and it can make it out to the right-hand side. So this operator here, this average null energy operator, this operator is, there are bounds on this operator normally, but those bounds use as an assumption the fact essentially that you don't have couplings like this down here, that you don't add couplings to your Hamiltonian at a given time. Now, one comment about this, it's extremely important that you deform the Hamiltonian at a given time by this coupling. So what you don't want to do if your goal is to have something go from the left side to the right side is just act with this unitary. This is a unitary. Just act with it on the thermal field double. That, if you evolve forwards and backwards, will produce a state where this particle will get hit by both a positive energy shock coming out this way and a negative energy shock going in this way. But the positive energy will always overcome the negative energy and will not allow a traversable wormhole. Okay, that point is will probably come up again. Okay.
So Adam, I have a very naive question. So does it depend on the sign of lambda?
Yeah, good. Sorry, I should have said that. Yep, thank you very much.
Yeah.
So there's a lambda out here. And indeed, the protocol only works for a specific sign of lambda.
Okay, thank you.
Sorry, I should have said that. Thanks.
Sorry, can you repeat again which operation we have to do?
Yes.
You distinguish acting with the operator from adding it to the Hamiltonian.
Good. So if you take the thermal field double, let's call it beta left right, and you just act on it with e to the I lambda k. This state, if you go and now you compute the expectation value of the average null energy in this state, it will always be positive. The reason for that is in the space-time picture of this state, there is a positive outgoing shock going this way and a negative ingoing shock this way. And the particle will get time delayed by this positive shock and time advanced by this negative shock, but the time delay will always overcome the time advance. Now, what you do to get around this is in the history of the particle at a given time, you actually add this term to the Hamiltonian. Well, it's not quite that simple, but you deform the Hamiltonian in a way that has the effect of essentially gluing on the stress energy in the state will be vacuum before this time, and then it will look like this deformed this state after t equals 0. So that the net negative energy will be so the net energy will be negative. Does that help? I'm not sure if that. Okay, if that satisfies you.
Is what you said that you want to sort of change the state by delta function instead of continuously by adding it to the Hamiltonian?
I think another way of saying this is that the space-time picture of the state that you end up with is not a state in the original theory. It is a state in a theory with a time-dependent Hamiltonian. That's all I wanted to say.
Isn't this, roughly speaking, proportional to beta, to the thermal field double state?
What? Sorry, what is?
This e to the I lambda kappa acting on beta is proportional to beta, right? If you're assuming it's a double chase operator.
Yeah. You mean to leading order? It will just be. Sorry.
Yeah, it's just a phase, right?
Yes, correct. Yes, that's right. Well, sorry. The precise statement, as I understand it, is that this particle, the message that you're trying to send in, its wave function will just get shifted by a phase in a certain limit. But that scattering matrix in this scattering event, that scattering matrix is just proportional to a phase to leading order. This is the iclonal approximation. Is that what you were referring to?
Oh, no, I'm just referring to this double trace operator acting on thermal field double state. We'll just give you some field double state.
Yes, right. You're saying because to leading order, this is essentially just the shift, yes, right. So in a certain approximation, this just becomes e to the I p plus times, times lambda, acting on the thermal field double, where this is the bulk null energy operator, which generates shifts, and this just preserves the thermal field double. Is that I think is what you're trying to say. So this is just. Okay. If there are any more questions, let me know. So good. So there's in SYK where all of the gravitational dynamics are just described by trajectories of boundary particles. We can do a similar thing. So we have a left boundary particle and a right boundary particle. And instead of tracking the trajectory of this message, instead what happens is the boundary particle trajectories can change. And so this message, when it falls in, at a given time when you deform, these boundary particle trajectories can move like such. And now this particle can reach the right boundary. This message can reach the right boundary particle. So that's sort of a nice simple picture for this effect in JT gravity. This is in JT gravity. So a natural question in JT gravity might be, is it possible to do a deformation that allows me to see everything on the left, let's say, from the right? So in other words, can I get everything that leaves the left boundary to end up hitting the right boundary? And a question like this was considered by Madeleine and Chi, and the answer was in some sense yes. And in fact, they can do really well. They can let the two boundaries be in causal contact forever after a specific deformation. So they created an eternal traversable wormhole, in other words. Okay, the example now I'm going to bring up is the one that is the most relevant for this talk. So there's a similar thing that you can do. This is drawing on recent work. So this is the example of what I will call the peninsula after their terminology. And this is due to Ahmed, Ragu, and Juan. So in this picture, we're again just working in 1+1D gravity. So the idea is you have a black hole, an eternal black hole, and you couple both the left and right boundaries to a bath. Okay, so the picture here is that I have flat space, and then in here I have ADS2, and then again I have flat space. So this ADS2 goes on forever, and the metric in here, and the dilaton in here is that associated to a black hole solution. So at inverse temperature beta. Okay. Now, the way to think about this is that it's dual to two quantum mechanics models coupled to BADS. So here's the left quantum mechanics model. Here's the right quantum mechanics model. So this is QM left, QM right. And these two pictures are dual to each other. Now, you can, in this picture, you can take regions of the bath and ask about what their quantum extremal surface or their entanglement wedges, are, right? So if we consider the region, the following region, let's call this region A, and then I'm going to draw an interval here on the right, which I'm going to call B. So I'm using capital letters to denote boundary or UV regions. So these are regions in the UV theory. So in particular, A includes this left quantum mechanics model, whereas B is just an interval in the right bath and does not include the quantum mechanics model. Okay. So over here in the gravity picture, what does this look like? So what happens is that AB now includes, so this will be AB. So what happens is that the left region on its own would just include this left exterior of the black hole. So let me do something here. So I'm going to call this A and this B, and this green, the union of the two green intervals is AB. On its own, big A over here, big capital A, just includes little a. And on its own, big capital B just includes little b in the low energy approximation. So, but if you take the union of the two, so if you take both A and B together, your entanglement wedge grows a little bit. It grows to include this peninsula here. And the way you find this is you solve the quantum extremal surface equation. So for those of you that don't know that, I'll just tell you. So in higher dimensions, what you try to do is extremize a functional. That functional is the generalized entropy, which is area over 4G plus S bulk. In 1 plus 1D, the dilaton plays the role of the area term. So what we want to extremize is the following quantity. And here it's S bulk of AB. And I want this to be 0. Okay? So this is the extremal surface equation. These primes I really should say D plus minus, D plus minus. So what I'm doing to find this equation is I'm changing the endpoints. I'm taking this endpoint here and I'm moving it up in this direction or in this direction, and I'm trying to extremize this function. Okay? Are there any questions about the setup here? So a comment that was pointed out, or an observation that was pointed out in this work was that what one can do to get, so say I on the right, I insert an operator down here, and that operator falls in. Maybe at first this operator is in this complementary region here. So maybe at first this operator is, say, there and can be reconstructed by the complement of AB. But as I move down, eventually, now if I insert the operator down here and then time evolve forwards, it will be lost from just this complementary region. It will now sort of be, you know, it will be reconstructible from AB, but it will be not reconstructible from the complement. Okay. Now, what they pointed out was that if I do a bilocal coupling on AB, so meaning if I write down an operator, which if I add to the Hamiltonian a term, you know, if I add to the pathing rule something like this, where again K is equal to integral, now it's O. Now what I'm going to do is O little a, O, sorry, O little b, then this will produce negative energy shocks. or pulses of negative energy that will pull this operator out. So it might send in a pulse this way that will allow this operator to reach the left boundary and be reconstructed on AB. But in order to do this, you had to have access to both an operator in both A and B at the same time. Okay, so this is a natural question along the lines of the questions that were asked by Mamasena and Chi is just, is it possible to come up with an operator K such that I can actually see everything that falls in here? Meaning I can send in enough negative energy that pulls everything that's in this entanglement wedge out. One comment about this is that, say we did not have the quantum extremal surface prescription. So say we had both A and B on the boundary, capital A and capital B, and we forgot about this term. Well, what we would find is that the entanglement wedge, or the wedge associated to AB, is just the left black hole union this interval here, right? But then you would get yourself confused, because there certainly are bilocal couplings between those two regions that sends in negative energy, right? And it would then be able to pull things out from outside of what you thought the entanglement wedge is. I say this just to point out that, so it certainly seems that the quantum extremal surface prescription is motivated by the fact that you can generate negative energy on these regions. And the question is the quantum extremal surface actually the region that you can see precisely by adding terms like this to the Hamiltonian? Is there such a term that can uncover the whole entanglement wedge? So right, so the question I want to ask is question, can we uncover the whole entanglement wedge this way? Okay. Are there any questions about what I want to do? I'm just gonna redraw this picture really quickly. Okay. So we have our region B. Any questions? I can, first, before trying to answer that question, let me just try to convince you that it's impossible given operators just localized on A and B. So just given A union B, it's impossible. Entanglement wedge reconstruction basically tells you that it's impossible to uncover or see more than the entanglement wedge. This follows from the fact, well, let me define something to convince you of this. So for those of you that don't know this terminology, I'm just going to define this. So there's something called the causal wedge. So given a boundary region A, the causal wedge, or CW as I'll call it, is the bulk region that lies in both the past and future of the domain of dependence of A on the boundary. Okay, so in this example up here, little a, capital A was this, right? The domain of dependence of capital A is just this, the the whole left exterior of the black hole, right? And in this picture, the domain, the causal wedge of B, right? This is B. The causal wedge of B is just the domain of dependence of B in the boundary theory. This is a funny aspect of these two-dimensional models, that it doesn't really have a non-trivial causal wedge. Okay, does that definition make sense? So this is the stuff in the book that can causally access A and causally be accessed by A, right? That's all this is. But the amazing thing, I mean, we're used to it by now, but we should still stress that this is a crazy thing, naively, is that entanglement wedge reconstruction tells you can do better than just the stuff you can access causally. And like that fact, I feel like, is at the heart of all of these recent developments regarding islands. They're just more pronounced there than they are normally, but it's still here in this example. So there's a proof. So there's a proof due to Aaron Wall and others. Also, it's just an intuitive proof that the causal wedge always has to lie inside the entanglement wedge, assuming certain bulk energy conditions. So this is true classically. Now here you might worry, well, you're explicitly violating bulk energy conditions in the protocols that you're doing. It turns out that that doesn't matter, because there are quantum versions of all of these that allow you, that prove this statement at the quantum level. And in particular, these theorems tell you that if the only thing you have access to are operators in A union B, then those quantum energy conditions should still hold, at least in an average sense. And so you can't get the causal wedge of A to exceed, or of AB really, to exceed the entanglement wedge. Okay. But yet these bilocal couplings, in some sense, are moving this causal wedge. They're moving it out, right? Because things that weren't causally accessible by A are now causally accessible, right? So in some sense, they're moving this causal wedge out deeper into the bulk. All right, so now what I want to convince you of is that this inclusion can actually be, well, at least in some sense, saturated. It's not entirely saturated, but I'll try to explain the sense in which it is. Okay, so all right, so now I'm going to turn to the main goal here. Are there any questions? So now my goal is to explicitly construct.
I have a question. When you are defining the causal wedge, are you allowing this bilocal operators or not?
Right. So I'm allowing bilocal operators in the region A, B.
Okay, thank you.
But yeah, good. So an important point is that if you allowed yourself bilocal operators, say on on the whole left and the whole right, then you can certainly move the causal wedge of A, B outside of its own entanglement wedge. But the claim is that if you're only allowed access to operators in A union B, then you can't move it beyond. Okay, so the goal is to explicitly construct operators supported only in AB that send in just the right amount of negative energy to pull everything out. To pull everything in the entanglement wedge, but outside the causal wedge, out to the boundary. Okay. So here, actually, let me do a trick. I think Ahmed once said that we need a stamp. Community needs a stamp, and maybe this this app has provided that for us. Okay. All right. So how much negative energy do we really need to be able to send in? So again, at some time t equals 0, what we're going to do, so at time t equals 0, we want to deform the Hamiltonian by some operator. Let's call it, again, K, right? And the stress tensor, the null energy in the bulk before that time, I'm just going to take to be 0 in the canonical. I should say that the state that's considered here, there's a Minkowski plane here, and the state is taken to be the vacuum on this Minkowski metric, okay, which is the canonical choice for ADS2. So before, the stress energy is going to be this, and then after, it's going to be given by, so this is t less than 0. Afterwards, it's going to be given by e to the ik lambda, e to the minus ik lambda. Okay?
Adam?
Yeah.
How much of what you're going to tell us do you think is specific to this 1+1 dimensional model that you're considering? Or is this just to be very concrete about the operators?
Yeah, sorry. I should say this is to be very concrete. This is still part of what we're trying to work out. We have some examples where it works in higher dimensions, but general prescription we're still lacking. So, but it's something to think about. But here we can do everything very explicitly. So for the purposes of this talk, let me just focus on this.
I'd still be interested whether you expect the basic result is always correct.
I think yes. In a specific class of examples, yes, I think the basic result will be correct.
Thank you.
I can, yeah. Let me come back to that at the end of the talk, when it's clear what might happen more generally. Good. So in order to get everything out of this entanglement wedge, how much negative energy do I actually need to send in? And ideally, what I would like is just a pulse propagating along the causal horizon of some amount. So if this is x minus, this is x plus, right? I want a pulse t minus minus that goes like delta of x minus times some number. Let's call it p minus for now. Okay. If I could construct such a thing, and if I can make p minus large enough, then I claim victory. And so what is the size of p minus that one needs to do this? Well, one way of seeing that is to actually try to figure out what the dilaton is doing in this region, right? So in the x minus direction, the dilaton obeys an equation like this. And it's going to be little a b. So just to remind you all, I'm calling this little a b, right? Now, this is where I am going to start making some approximations. So I should say what I'm saying today, maybe this is actually something I should have said to Raphael, is to leading order in a couple of parameters. So it's to leading order in G Newton. So and it's also to leading order in C times G Newton. So C times G Newton, but I'm also going to take another parameter small, which is 1 over C. So I want to take the following limits, C just less than 1 over G Newton. C here is the number of light bulk fields that I have. So for if you really want to be concrete, you could follow what was done in a recent paper by Yiming Chen, where he took the bulk to be a 2D free massless fermion. We're going to consider a theory of K free massless fermions where K is very large. Okay, or 2C free massless fermions where C is very large. Okay. So in that approximation, what I find is what we can argue is that this derivative for AB is actually just, to leading order, just the derivative of the following in the bulk. Let's call it AB, where AB is little a is this and little b is this. So A is really just the causal horizon. So plus terms that are order C times G Newton squared. Or sorry, these will be these will be order 1 over C to the 0 in this case, but they'll be high order in a 1 over C expansion. Okay. And then I can use the fact that there's a symmetry to this state. So there's a symmetry here that this horizon has, which allows you to rewrite this as partial S bulk just of A plus S bulk of B. Sorry, I'm going to put minus signs here. Plus partial S bulk of AB. Okay? So this term is 0 by symmetry, right? Because this is a causal horizon, and this term, this is a 0 expansion causal horizon. So this state, or put another way, you could just explicitly compute this, and it's always going to be 0 in the CFT. And this term here is just 0 because we're not moving any of the endpoints of B. And so what we get is actually that this is equal to minus the derivative of the mutual information in the bulk between little a and little b. Okay? Now, what we need then is a shock. What we would like, so by the way, this by inequality called Strong's additivity, this is actually positive. Okay? The mutual information decreases as you shrink one of the regions. So this is always decreases when you shrink one of the regions. So this is a positive quantity, which means that the derivative of the dileton at the quantum extremal surface is equal to the derivative of the mutual information to leading order, which is negative. So the dileton moving in this direction is decreasing. Okay? So that means in order to get everything out, what we want is for the dileton to actually end up going from having negative expansion here to having 0 expansion. So if it goes from having negative expansion, moving off of this quantum extremal surface, gets hit by a shock, and then has 0 expansion, that means that it won't, in other words, in analogy to higher dimensions, it won't focus before it hits the boundary. Right? So I'm assuming here that there's no other energy propagating in the space-time to the future, right? So if it's really just a shock, that shock just needs to have just the right amount of energy to cause the dileton to go from negative expansion to 0 expansion precisely. Okay? Now, how do I do that? Well, that means I want across the shock, I want this to be the case. So I want the dileton expansion to increase by precisely this amount. And you can find an equation like this by integrating the equation of motion for the dilaton, if you have a stress tensor shock, T minus minus of X minus is equal to delta of X minus times D minus I of AB. Okay? And note that this is a negative quantity, so this is a negative energy pulse of, this is a negative energy pulse that you need. Okay? Does that explanation make any sense? I'm inferring causality properties from the behavior of the dilaton. Perhaps some people who are less familiar with higher dimensions might have gotten lost by that. But does that make any sense to people? Okay. Good. So now what I need to do is construct a state with this shock, and that's just a problem at the level of bulk quantum field theory. So let me back up for a second and move away from gravity and just try to construct such a state in quantum field theory. So now let's just move back to QFT and try to construct the state. Okay. So the claim is that the bilocal operator that does the job, that creates this pulse of negative energy, is E is K. I'm going to call it KAB. I'm just going to call it CAB for reasons that will become clear. Is log of the density matrix on AB minus log of the density matrix on A minus log of the density matrix on B. And there should be tensor identities on the other factors here. Okay, in quantum field theory, just as an aside, in quantum field theory, these guys are well, density matrices are not well defined in quantum field theory because of UV divergence issues. But everything I'm going to say can, and in the paper, will be upgraded to the realm of algebraic quantum field theory. But for the purposes of this talk, let me just use density matrix lingo because everybody is relatively familiar with that, and just makes the presentation easier. So if your issue is about UV divergences, then know that probably will be resolved in the end. Okay, in other words, all the quantities I talk about are well defined in the continuum limit. So note that this is an operator in the algebra of operators on AB, right? So this does the job. And and the thing I'm going to consider is the unitary that's generated by CAB. For people who are algebraic quantum field theory enthusiasts, this is what is called the Kahn's cocycle between the vacuum and what's called a split vacuum on A and B. Okay, I'm not going to say anything more about that, but if anyone knows what that is, that's what it is. As an aside, this object or objects similar to this have been studied by in a nice paper by Sehan Faulkner and also by Nima Lashkari and a whole host of other people. Although those are the people in our community that have most recently been studying this object. But okay, so a few facts about this operator. So this operator does not factorize between the two regions, so that's good, right? It better not factorize if we're going to get any negative energy out, right? If it factorized, we wouldn't have any correlations between the two sides, and or the operator wouldn't effectively have any correlation between the two sides, and so it wouldn't create negative energy.
Do you mean a plus sign in this formula?
Where?
In one, do you mean a plus sign so that the exponentials are 2 factors? Or?
I think I mean a plus sign. Yep, thanks, sorry. It does not equal this. Yep, sorry, thank you. I meant the unitary. Yeah, so the unitary that this thing generates does not factorize into a product of unitaries, one on each side. Yeah, thank you. Sorry. And the second fact about this operator is that its expectation value in the vacuum is equal to the mutual information in the vacuum between the two regions. Okay. All right. So what I'm going to do is use this operator to construct states with shocks of energy that have the requisite size. So what I'm going to study, so states. So I should say what follows is very closely, this is based upon, it's based closely upon work by Sahan and Faulkner. So the state I'm going to study, I'm going to call omega s, which is just e to the I CAB s acting on omega. Okay, so this is just to remind you, so this is sigma A to the IS, sigma B to the IS, sigma AB. And the picture I'm going to have for now, I'm just going to work in 2 dimensions, and I'm just going to work in a conformal field theory. That's for simplicity. It'd be interesting. We haven't studied these states in full generality, partly because they're very hard, and I'll explain why they're hard in a second. But this is the setup I'm going to consider for the talk. Sorry. So I have 2 intervals in a 1 + 1 DCFT. I'm going to call this one A, this one B, and then the complementary region will be C. Okay? Now, the idea here is that, so let's study this state, expectation values of this state. So a few facts that I'm going to need. One is that operators flowed under the vacuum density matrix on A. So local operators in A just get translated along a local flow. So in particular, the flow looks something like conformal. It's a conformal killing vector in this region, and it sort of is just conformally boosting all these operators, right? Similarly for B, same for B. Okay, this is special to 1 + 1D conformal field theories. But what is not true, sigma AB to the IS generates a non-local flow. So this non-local flow is highly theory dependent. And in certain cases, like very special cases, like for free scalars or free fermions, it's been understood. But in general, it's a really hard problem, and we don't really know how to tackle it. But here, I thankfully actually won't need to know much about it at all. The reason I won't need to know much is a fact. So if I act with this guy on the vacuum, I can actually just replace this with the complementary density matrix acting on the vacuum. So this is a fact about any state of full rank. So meaning its density matrix has full rank, then you can do something like this. So using this fact, let's try to compute some stuff. Sorry. So this is just equal to sigma AB to the IS, sigma A minus is, sigma b to the minus is. Okay. Now these commute with sigma a and OA, so they come through and kill each other. And now sigma AB on either side, I can swap them for sigma C's, which also commute with everything, and so they also disappear. So all I get is just sigma A to the minus is, OA, sigma A to the plus is. Okay? So expectation values of operators in A just get boosted. An exactly similar argument for B goes through, and so expectation values of operators in B also get boosted. Also, expectation values of operators in both A and B, so correlation functions between A and B, these also just get boosted. So what you get is just omega OA S OBS, where I'm just using notation to define the modular flow for each individual region. Okay, but also operators for an obvious reason, expectation values in OC are untouched. Okay. So that means this state, going back up here, this state is just doing boosts in either region and leaving everything else unchanged in C. Now, I should say when I mean everything else, I mean everything in these causal diamonds for C is unchanged. Up here in these regions, all hell can break loose. So we don't know what happens up here, and it's highly theory dependent. In part because, as we'll see, this state has shocks propagating along all of the boundaries of the domains of dependence. Okay. You could tackle these regions if you had control over this. Those two problems are linked. All right. So now to compute the energy density, we use a trick. We follow this paper by Sehan and Faulkner, and we just use a trick which they called the sum rule. So let me just briefly try to tell you how this goes. It's a little bit technical, so if you don't follow everything, it's not super important, but I'll highlight the final result. Okay. So first, I need to know the following object, which is called the relative entropy between two states, which is trace rho A log rho A minus trace rho A log sigma A, where these are density matrices on A, right, on sigma. So log sigma A, or minus log sigma A, we call the modular Hamiltonian on A, okay? And this has a nice form in general for Rindler wedges and things, and in a CFT, anything conformally related to a Rindler wedge, this thing will have a nice form, okay? In particular, the form for a Rindler wedge is just, so if my Rindler wedge goes from x plus equals 0 to out to infinity, right? The modular Hamiltonian just takes a nice form, which is just the boost generator of that Rindler wedge, okay? I should say, when I write this formula, there's a vacuum subtraction that has been done, which will be important in a few minutes. Okay, using this, I can try and, one thing to note is that for a general position of this Rindler wedge, I just shift everything up, right? Like this. And so now I can take derivatives of this guy with respect to moving this region around. That will be useful because of, well, because we were instructed to consider such things by quantum extremal services, but also you can write a nice formula which looks like the following. let me always denote the vacuum by omega. Sorry, this is the, sorry, I should have said, this is for vacuum as a nice form for the vacuum. That's very important. In general, it does not have a nice form for general states. Right. Where A bar is the complementary region of the Rinder wedge, right? So if this is A bar is over here. Okay. You can work this out, and if you use, so using purity of the global state, you can argue that this is actually just equal to the stress tensor, or you can compute that it's just equal to the integral of the stress tensor along this horizon here. Sorry, let me redraw this picture. So we have a bar. The difference of these two terms is just an integral of the stress tensor along. Okay, this was just a little warm up, but now the sum rule. So this is a sum rule. It's a sum of terms that equals a positive thing, and note that the positive thing is independent of the position of the Rinder wedge. So the one that will be useful for us is slightly different, and I actually don't think it's been used much. Yeah, let me just say this. So now we're going to move back to this example with two regions. And we're going to write down the following sum rule. Okay, so again, let me go back up here. Sorry. So this setup should be in the back of your minds, right? And what you can work out is that this is actually equal to the derivative of delta of the modular Hamiltonian on C in the psi state. So this is a vacuum subtracted expectation value, and delta on HB. Hang on, I need to tell you something. So what I mean here is I'm taking the endpoint of B here, and I'm shifting it up. I'm looking at derivatives as I move in the x plus direction, right? So this sum rule is what you get for those types of derivatives. Note that A has dropped out because I'm not touching A's endpoints. I'm just moving B's endpoints, so only B and C are left in the end, okay? So this is true for any state, and what I'm going to do is use it in, so I'm going to set psi equal to our omega s state, and I'm going to try and study it in that state. And I should say, in 2D CFTs, this guy and this guy, so this right-hand side, is just an integral over this null plane, this null line. So it's an integral, let's call this null line, let's call this C minus, and then we'll call this B plus. So it's integral over C minus of T plus plus, plus an integral over B plus of T plus plus, and there are functions in here which I'm not going to write down because they're not really important for this discussion. But the point is that you get this sum of three derivatives of relative entropies equal to just an integral of the stress tensor, a local integral of the stress tensor along this null line segment here. Okay, it's exactly analogous to the Rinder case. Okay, and now what I'm going to do is, again, consider S of rho A. So what I want to do is understand derivatives of the relative entropy in this omega S state. So what I'm going to do is consider something like this, right? So this is the object that we need to understand, where now B tilde is some slightly smaller region in B, okay? So I want to understand what happens as I change B tilde, the position of B tilde, let's say on the null horizon, as I move it up or down, what happens to this quantity, okay? And what I can argue is that in these states, at least when this point here is very close to this corner, these states are, these relative entropies in the omega S state is approximately equal to sigma A B tilde omega e to the minus 2 pi s sigma A omega tensor sigma B tilde e to the minus 2 pi s omega, where what I mean by this is that I just take the x plus coordinate and I shift and I multiply it by an overall factor of e to the minus 2 pi s. So remember, the s is how much modular flow you've done. Okay, but also remember that we've left C untouched. So that means also S of rho C omega S in this is just equal to S of sigma C omega, sigma C omega, which is 0. And so actually, if I go back up to this sum rule here, this term drops out, and this term has a nice form in terms of vacuum mutual informations between different regions. Okay, and when all the dust settles, what I end up with is the following answer: that this whole side here of this equation just becomes e to the minus 2 pi s times a null derivative of the mutual information between A and B. I've now in the end set B tilde equal to B, is equal to these local integrals of T plus plus and T plus plus in the omega S state. Now, in C, 1-point functions are left unchanged by this flow, right? So this is actually just the vacuum answer. And here, 1-point functions are just dragged along these conformal killing vectors. So this is effectively just a vacuum expectation value here. And naively, what I find is that this term is 0 and this term is 0. So then I get confused. Well, the mutual information derivative is 0. The answer is that actually you need to be careful about the endpoints of these integrals here. And there's actually a shock that you can figure out is there, and the shock precisely has the right amount of. Sorry, I missed. This is not quite right. When the dust settles, the answer is e to the minus 2 pi s minus 1. So when the dust settles, you find that the stress tensor has this form. Okay, where the delta function is centered along this x plus coordinate. All right, if you didn't follow the details, that's fine. I doubt many of you did, but the point is just that the stress energy in this state has a delta function pulse, and in the large S limit, it has precisely the right magnitude for what we wanted. Oh, sorry. There we go. It has precisely the right magnitude that we needed to get everything out from the entanglement wedge. Okay. And doing similar analyses for other null directions and for A as well tells you that actually there are pulses of energy propagating along all of the boundaries here. and they all have an amount that's proportional to derivatives of mutual informations. But over here, the derivatives are with respect to moving A's endpoints, whereas over here, they're with respect to moving B's endpoints. Okay. Does that make sense? I'm running a bit short on time. So let me just briefly move back to the gravity example that I focused on, and then I'll be done. Okay. Does anyone have any questions before I do that?
So, Adam?
Yeah.
This looks vaguely similar to some shock that Sahan and Faulkner, or that you can deduce from results of Sahan and Faulkner for their flow. Is the fact that a derivative of the entropy here gets traded for mutual information just the particular combination of intervals that you're considering?
Yeah, it's just the fact, it's just the states that I'm considering in the flow. So for Sahan and Faulkner, they considered a co-cycle between some excited state psi and some in the vacuum, let's say, omega. I'm considering a co-cycle between the vacuum and some split state between the two regions. So this is in my example, the vacuum is playing the role of an excited state for Sahan, in Sahan and Faulkner's language. Also the added also they only in their wedges, and we're considering these intervals, but the general structure is almost exactly the same. In fact, in this discussion of split states, there's a unitary. So I don't want to get too far afield, but there's a unitary that can map you from the vacuum. So there's a unitary that maps you from the vacuum to 2 copies of the CFT, and it maps you to an entangled state on CFT tensor CFT. So this is just on the CFT, and an amazing fact in quantum field theory is that there's a unitary that takes you to a doubled picture of the CFT, and it's a unitary, not an isometry, a unitary. And in that setting, if you take our whole procedure and use this unitary to map it to the doubled picture, then it really does look exactly like Sahan and Faulkner, because this state under the unitary gets mapped to the doubled vacuum.
Thanks, that's beautiful. Thank you.
Okay. All right, so back to that gravity example, to the peninsula case. So, so what happens now is, well, sorry, let me, so we have this peninsula here, and when we act on the boundary with this flow, you can try to sense this this negative energy pulse and see that it's propagating along the causal horizon. And one way of doing that is to compute a double-sided correlator. And what this correlation function ends up being in the deformed theory is psi left of t left, e to the I c a b s, psi right t right, e to the minus I c a b s. Or written in terms of density matrices, it's really this: sigma a is, sigma b is, sigma a b to the minus is, psi right t right, e, sorry, and then the same combination of density matrices over here. Oh, one comment I should make. Sorry, but before I forget, this energy, so this energy is for positive S, this coefficient out here is negative, right? And this is negative, so this is a positive energy. But for positive S, this coefficient out front is positive, this is negative, so this is negative energy. This is exactly analogous to how in Gauss-Jeffers wall, the coupling, the protocol only works for certain signs of coupling. So what's sort of funny about this is that normally we think of modular time as being an analog of time, but here it's playing the role of a coupling. So yeah, sorry, let me, okay. And right, so this correlation function is actually something that has been studied before in other contexts by Tom Faulkner and various other people. And it's actually sort of, its structure is basically that of an out-of-time ordered correlator. And it's sort of it's a hard thing to compute in general because we don't have control over this, over this two-interval modular flow. But if one goes ahead and computes it in, let's say, in a bulk theory, which is just a free fermion theory, which you can actually explicitly do, then the answer that you get, at least to leading order in these parameters I was talking about, so at least to leading order in G Newton C and to G Newton, this object has exactly the form of an out-of-time ordered correlation function, where this, where these operators are probing a shock of precisely energy equal to the derivative of the mutual information. So I just say this as another way of trying to understand the bulk dual of these states, and this is something that you could try to do, which is compute this out-of-time ordered correlator explicitly. Okay. Good. I think that's all I wanted to say. Let me just say some future directions or open questions where I'll come back to what Raphael asked. So far, everything I said in the bulk, in these explicit examples at least, was only to leading order in these small parameters. It would be interesting to ask whether it makes sense to go to higher orders, or what happens to this protocol at higher orders. So it just does it just break down? Yeah, I would like to know that. So what happens at higher orders? Yeah, and other more general scenarios. So
would you repeat that's why you needed large C?
Yeah. Sorry. I think you might actually be right that I for what I described, I only needed a small C G Newton. Well, sorry. Yeah, it's just that you want the entanglement. Yeah, good. The intuition that I have is that this entanglement wedge here needs to be order, this entanglement wedge has some fluctuations associated to it. The geometry, or in JT gravity, I guess the boundary particle trajectories are fluctuating. And you need to worry about if this position of this quantum extremal surface here is actually well defined. And I think the large C approximation will tell you that this distance is actually sort of a meaningful distance. That the fluctuations of this surface are small compared to the position of the surface. I thought 1 over C.
Okay, thanks.
Yeah. All right, so other more general scenarios. So for example, what if we don't have a union of 2 intervals on the boundary, but say we just have 1 interval, but we have an excited state, right? So say we have 1 interval, this is my boundary, this is time, this is like Z equals 0, right? And I'm gonna draw the causal wedge of my boundary looks like this. my boundary region, and then the entanglement wedge has some funny shape. Let's say it's, you know, they're macroscopically different. What is the analog of what I discussed today in this example? We think it still might have something to do with this co-cycle flow between the excited state and the vacuum on this interval, but that's something we're still exploring. And the other really interesting question is what is there some kind of picture we can draw when we don't have a peninsula, but we actually have an island. But have an island. Yeah, this is very interesting to me. It's possible that there's just no semi-classical picture, and actually probably likely. In fact, I think one could just argue that that's the case, but maybe there are certain special classes of examples where even with an island, this modular flow has some kind of semi-classical description. Maybe that's too hopeful. I don't know. And then finally, is there an argument from the boundary? Why did this have to work? Right now, it just sort of seems a bit like an accident, but it's possible that there's a nice quantum information explanation for why this whole protocol was the thing that produced the right amount of negative energy. Okay, that's I think all I want to say. And yeah.